So we're doing related rates. So related rates is something that we've talked about before, but not in this detail. So the example was before was with the snowball, and I gave you that if I was building the snowball and making it bigger and bigger, if I knew how the radius was changing, then I would know how everything else on there, the volume, the surface area, the circumference, everything about the snowball, I would actually know what was happening on there. So the thing is that with the snowball, we're not going to have like X as a representative anymore. So as I'm building the snowball, what is actually changing is the time. So as time is passing, the snowball is getting bigger. So now we're going to use implicit differentiation because we're no longer going to be using the derivative with respect to X, which is what we've been doing. We're going to do it with respect to T for time. So what is the rate? If I know the radius at T is equal to 5 seconds, at what rate is the volume changing at T is equal to 3 seconds or 4 seconds on there? So we're going to be able to use that information and find out the related rates between problems. One of the easiest ways to think about related rates is the ladder problem. And so here's an example of the ladder problem. And here are some steps that you have for the related rates 1 through 5 that you can look at it. Those are found in your booklet as well. But let's look at exactly a visual of what is actually happening. So here's the wall that we have here, and here's the ladder. So if you notice, the ladder is not going to change size. So if I move closer and closer to the wall, the ladder climbs the wall, and so therefore this here, the H in this problem, is going to get bigger on there. But if I get further and further away from the wall, that means the ladder is going to go with it, and the ladder is going to be coming down the wall, but it's getting further. Now direction is going to matter. So if I'm going up, that means it's going to be positive for the height is increasing. But if I am moving further away, the height is getting smaller. So they're related. So whatever happens to X is also happening to H. That's what a related rate is. When something happens to one, it's also going to happen to the other. They're not independent. So when X is getting further away from the wall, we say that that's the positive direction. And then, so that's going further and further away. It's the positive direction. When it's getting closer and closer to the wall, that means we're subtracting the distance, so therefore it's the negative direction, and it's easier to know which is the direction from going up or down on the wall. Up is positive, down is negative. So that's what we consider related rates. And so when we look at a problem like the one that's in your booklet here. And so if we look at this problem, we have that Alex is on looking at a building into seeing and spying on his enemy, and Ben is sitting, his accomplice is not sitting, standing 6 feet away from the wall. And the problem is asking that if Alex starts and the ladder starts to slide down, at what time is it going to hit, or the velocity, at what rate is it actually, the ladder going to hit Ben? And so I know this is a crazy problem, but that's what it's actually stating. So that's what it's going to fall and hit Ben on there. And then notice how it's against the wall. So if it's forming a right triangle. So those are the things that you want to look at. So here, the ladder is not changing. The ladder is staying the same. But what is changing is, in this case, we call it y, and this is x. It's the y and x values that are changing. So what we have here is the x value and the y values that are changing. So what equation can I write this? Well, this is the right triangle. So I could write something that is going to give me the right triangle. So the legs are x squared and y squared, and we have that the hypotenuse, or the ladder, is 10 squared. So that's what we have there. Now we're going to take the derivative, but oops, and we're missing something. We're going to do it with respect to time, because as time is passing, then the ladder is falling faster or slower, because it's going to pick up speed on there. So differentiating both sides with respect to t, that's missing on mine, but it's in your booklet, or respect to time. So now we're not doing with respect to x. So we have to take these in the derivative with respect to time. So we do the chain rule. So we take the derivative of the outside, which is 2. We leave the inside alone, which is x, and then we take the derivative with x. And so we're going to have dx dt there. And so that's a derivative of x squared. And then plus, so we have to take the derivative of the y. So it's going to be 2y, and we're going to have dy dt. And then the 10 squared is just going to be 0 because the derivative of 10 squared or 100 is still a constant, so it's still going to be 0. So this here is what the derivative actually looks like because we're taking in the derivative with respect to time. So now what are we trying to find? So restate the problems in terms of the rate of change. So what do we have? What are we trying to find here? We're trying to find out how fast, so that's going to be the rate, is the ladder going to hit bend? How fast is the ladder moving? So what we're actually looking for is this distance right here. And so what we want to know is how fast it's going. So it's going to be how fast is the x when time is passing. So the change in x over the change in time. So how fast is it moving? So we want to find dx dt given that. And so now we notice that the rate here, this is going to be important. They're giving us that when it is sliding down at a rate of 4 feet per minute. So that's your rate there. Notice how there is a positive 4 up here, but when we have it here, it's a negative 4 because when we're writing words, we never write down negative 4 up here. We always use words to describe it. So what this is going to be a rate. So this is telling us that this one here is going to be my dy dt. So that's the rate at which it is falling down. The change in y over the change in time is going to be negative 4. And at the instant when, well, what's the distance that I wanted to hit? It's going to be 6 feet. That's this. And so that's when we want to find out when x is equal to 6. So that's what we're looking at. And so I have the equation that we have here. And so we're just going to then substitute in the given values. So we're going to go on here and fill in this here. So we know we're given 2, and then the x that we want is going to be 6. So we're filling that out. That's when x is going to be there. And then it's going to be the dx dt. That's what I want to find out. So I am going to put that in there. So that's going to be the dx dt that we're going to try to find, and then plus the 2, and then the y. Do I know how high the y is? And from what it's given to us specifically, it's not given to us, but we could actually find it. But we're also given the dy dt, and the dy dt is going to be negative 4, and then it's going to equal to 0 because that's a derivative on there. But how do I find the y? Well, that's mathematically what we're going to be able to do over here. So we know that this is the Pythagorean theorem, so x squared plus y squared plus y squared is going to be the ladder squared. So I know that's going to be 100. Well, I want to know the y when it is actually the x is going to be 6. So I am going to put that there. Y squared is equal to 100. Bring that over 36. So it's going to be, when you do that, it's going to be the 64, square root of 64, and it's plus or minus, but we don't need the minus because we're talking about a distance there in this case, and so that's going to give us an 8. So that's what the y value is. It's 8. So notice how this is going to give us negative because it's a negative 4 because it's falling, but what we're really going to do is when we move it over, it's going to be so when we move it over, we know it's going to be a positive 64, and this gives us 12. So dx over dt is going to be 64 over 12. So you could reduce that on there to 16/3, or you could have that on here when we put it on the actual solving part, it's going to be 5.3 feet per second. So that's the rate that the x values are changing, or how fast the ladder is moving horizontally when it hits bend. So that's the instantaneous rate at which it's the speed that's going to hit bend on there. And so that's really what it's telling us on this other part right here. Where is it? Here it is. So that's really what it's telling us, and then that's the speed. And there's some more examples here that we could actually look at and see. We could do one more problem on here and say, suppose at the bottom of the ladder, and this time we're going to talk about this ladder that's here. Suppose at the bottom of the ladder is 5 feet from the wall. So let's say that, oops, that it's 5 feet from the wall. There it is. And so and it slides away from the wall at a constant rate of 3 feet per second. So you have to decide, is this going to be positive or is it going to be negative? So since it's sliding away from the wall, we're increasing the distance away from the wall, so it's going to be a positive 3 feet. And we want to find the velocity of the top of the ladder at t equals to 1. So at 1 second, when it passes 1 second, on there, we want to know what the distance is going to be from what the velocity is on the wall. And so if I am going to be moving, that means that it's getting further and further away here, that what is happening here is that the height is getting, it's decreasing. So it's the rate is going to be not positive, but negative because the ladder is falling. So that's what we know on there. And so how am I going to figure out what's happening at 1 second? Where will that X value be? And so in order for me to find out where that X value would be is that I know that the rate of the X values is changing at 3 feet per second. So at t equals 1, X is going to be 8. So that's where X is going to be is 8. So if I move this over here, notice how it's not falling that fast right there. So I am going to be looking at something that is probably not going to be bigger than 3 feet per second. So I know that X is going to be 8 when I want to find out at what rate, the instantaneous rate that it's falling there. So let's do that problem. Let's go back to here. And that's the problem that we are talking about right there. So let's work that out. So we know that we want to get here that the ladder, when it falls, it's going to hit, um, it's going to hit 8 right there. Because if this is falling at 3 feet per second, at 1 second, it was at 5, at 1 second, now it's going to be 8 feet away from the wall. Okay, so suppose that we have this ladder. What information do we have? We know that the ladder is 16. We know that the ladder is 16 feet. We know that the distance that we're going to have is going to be now 8. And so that's going to move the ladder down this way as we saw on that. So this now is going to be the new triangle. I know that this distance there is going to be 8. And then we need to know how high that is. So we need to know what h is there. So in order to solve that, we know that we're going to have h squared um, plus 8 squared is going to be 16 squared. And so when you solve it, we're going to get h is going to be the square root of 192. So now we know what h is, and so we're going to be able to follow this along and have the same thing. X squared plus h squared is equal to 16 squared. And so we're going to take the derivative. So it's going to be 2x dx dt plus 2h dh dt is equal to 0. And so then we start filling in the information that we have. So we have 2, and then we have that the x is going to be 8. The rate at which it's going is going to be positive 3 feet per second. And so we have this 2, and then we know the h is going to be the square root of 192. And we want to know how this one here is going to fall. And so what you do is you move this over. Notice how this is positive. So when I move it over, it's going to be negative. So I'm going to have 2 square root of 192 dh dt. And then when I move it over, it's going to be negative 48, which makes sense. And so therefore, when I put this into my calculator and divide the negative 48 by that, I'm going to get approximately negative 1.73 feet per second. Now, all of these require word sentences, so you would say it is falling at negative 1.73 feet per second. That makes sense because the ladder is going down. And so that pretty much does it all. Okay, very good.